This will be the last video for section 3.3. What we have, the final piece, there is a way to connect the second derivative back to the local extremes. So I do want to cover this, but you'll see as I go through, I do not think this is our best technique. I really think with all the ideas that we've established in 3.3, I think it's very important for us to keep the ideas of increasing, decreasing, and local max min, all those which go with the first derivative and connect to the original function, keep all those together, and then use the second derivative for all the concave up, concave down, and for the points of inflection questions. I think that's a nice way to keep everything organized, to keep us on track, and that we have as little confusion as possible. However, there is a way to use the second derivative to talk about local extremes. What we will do, I will establish the idea quickly and show you two quick examples. And through those examples, I'm going to also try and establish why I prefer what we were doing earlier, which formally we were using the first derivative to figure out local extremes. Technically, that's called the first derivative test. That whole idea I was telling you about how in the book, they make the box. If the first derivative goes plus minus, it's a max. If it's minus plus, it's a min. That technically is the first derivative test. So how does this test work? We will still, step one, find the critical values. So we'll still have to take the derivative, set it equal to 0, the first derivative I should say, set it equal to 0 and solve. But then we will plug the critical values into the second derivative. And here are the different results. So if my critical value is a value a, I will get that, f double prime of a will be greater than 0, f double prime of a will be less than 0, and f double prime of a equals 0. If f double prime of a is greater than 0, that means the function is concave up. You know you have a critical value, and you know your function is concave up, therefore that critical value, that value a, must be a local minimum. If the second derivative of a is less than 0, that means the second derivative is negative at this coordinate a, then we would get concave down, with a being the critical value right here. So that would establish a as a maximum. And now you would think, a lot of us logically would say, okay, well, when the second derivative at a equals 0, that means a is neither. But what we actually get out of this is that this is inconclusive. You tried using the second derivative test, but you'd have to go back and use the first derivative test to know for sure. So that's one of the reasons why I'm not a huge fan of the second derivative test. We make our first derivative test interval, we will get an answer for every critical value. We'll know every one, max, min, or neither, very clearly, and we'll never have any of that ambiguity that goes with this inconclusive step. So that's the idea. And like I said, let me just point this out, and I'll again use some functions we've already looked at. So we looked at the function, again, let's go back to the find where does the function have local extremes. Max min. And let's start off with that same a of x is x squared minus 4x plus 3. This one, the second derivative test will work. I mean, it will work for the others as well, but this one won't work well, but it's only because this function was so basic. The first derivative, 2x minus 4, I set that equal to 0, I get a critical value of 2. But now I'll take the second derivative, which is positive 2, and then when I plug the second 2 into the second derivative, well, there's nothing to plug in, so that positive means my function is concave up, so at that value 2, that must be a minimum. The only reason that works so well is because this was such a simple derivative. I mean, going from the first derivative to the second derivative, that's about the easiest one we possibly could have looked at. That's the only reason this works so well. Now, I do realize the book likes to show you this. When we get to some word problems towards the end of chapter 3, some of those word problems, we do end up with derivatives that are this simple. So it's not the worst thing to think about, but I don't think it was that hard to make the test interval and just go through. Again, we had 2, we had our first derivative, we went minus plus, so we got that same basic picture, and that's how we knew it was a minimum here. But now all we have to do, just look at the next problem. We did this function, and we did this work. Derivative wasn't that bad, but all the factoring and solving, this should not have been a terrible test interval to make. And then interpreting the signs, going up, going down, max, down, still down, neither, down to up, that one was a minimum. So we did that before, but look at what would happen. You would have this derivative, these are your critical values. You would need a second derivative here. I'm sorry, let me do that again. We had this first derivative, all this work to get these critical values, but now I'd go back to this form to take another derivative. It's not the worst. I'd have b double prime would be 20x cubed plus 30x squared minus 30x. So the second derivative itself wasn't that bad, but now I'd still have to plug these x values in. Plugging in 0, hey, you get 0. So that tells me nothing. I'd have to go back and do all this work to know for sure that 0 is a neither. So again, that's a big flaw. You want to use this, and the first critical value you have, you get inconclusive. But then the others, well, what happens when you test minus 3? What happens when you test positive 1? You have to do a lot of arithmetic here. So all these things, when all we were was just setting up our signs to be able to finish this and use the first derivative test. And then, not to mention, you start going to the next two that we did. Now, if you want to take another derivative, you could do this fairly quick, but if you come here, you've got quotient rule. In this one, you want to take a second derivative. Now you've got double product rule. So it's just so many situations where the second derivative test, sure, it does work, but our first derivative test is just a lot more friendly. So again, not bad. In your homework, there are a few problems that specifically tell you use the first derivative test for local max min, use the second derivative test. I think it's worth trying a little bit, but I strongly recommend to really stick with the first derivative test. I will never tell you on a test to use the first or second. I'd leave it up to you, but I think most students are better off using the first derivative test.